So SpaceHeroes CTF just ended and it was really fun. It lasted from April 1st to April 3rd. And like usual, I participated with my team, Court Corrupt, and we just had an overall blast. I personally tried to focus more on the pwn challenges because that's an area I'm looking to improve. And although I didn't get too many pwns owned, I am proud of what I did get, and that's my main focus today. I will be making write-ups. So I'm just going to copy the binary into here. And here we have it. Let's run it. And we see it prints out some ASCII art of Darth Vader. When I left you, I was but a learner. Now I am the master. Feed some input. Let's see what happens. Nothing. All right. Let's take a look at what's inside this thing. Let's open up Ghidra. And Ghidra is a reverse engineering tool, kind of like Binary Ninja, except not as cool and intuitive with all the features like an interpreter and stuff. Actually, I do think Ghidra has an... I'm new to this stuff, so I don't really know a lot. I think Ghidra has an interpreter, though. Whatever. The point is, it has a decompiler, so it can look at the assembly, and based off of what it reads, it could try to print out something similar to the source, which is useful for what we're trying to do. Alrighty, let's analyze, okay. Read all the symbols and stuff. And let's open up another window, make an exploit script. So we'll just put our classic shebang. On pwn, import all. And we'll get the elf, so Vader. We'll make a process from it. And at the bottom, we'll make sure we finish the script off with interactive. So let's look at the source. Let's see what functions we have here. We have print Darth. That just puts the ASCII art to the screen. We have ignore me. It looks like it's just clearing a buff. I'm actually not 100% sure what this does, but I'm just gonna do what the name says and ignore it. And we have main. We see we have a local 28 here. When I left you, I was but a learner. Now I am the master. And as we can see, we have an out of bounds write. We're taking up to 100 of the user input and storing it into this 32 byte character array. So let's see what other functions there are. Vader. So we see we have the Vader function here. And what it's doing is it's initializing all these variables, and it's initiating a flag variable. We can see here that this file is actually the flag, and it just prints it out to the screen. But furthermore, for the code to get to this point, all these conditionals need to be passed. And what it's doing is it's comparing strings in the parameters of the function call to these words. So what we can do, we can use some return-oriented programming to set all the registers that are used as parameters in the x64 calling convention to the corresponding values. And then at the very end, we can call this Vader function, and all these checks will be passed, and we'll print out the flag. Now, what you could also do, which is much easier, is when you overwrite the return address in main, you could just straight up put the address of like right here, right? We could just put the address bypassing all these checks. I don't know if that's the way it was intended to be done, or if they wanted you to do ROP. I'm pretty sure they want you to do ROP, otherwise why would they put all these parameters? But I'm just going to be doing it the ROP way. You could easily just overwrite the return address, and mostly because it's an educational experience to try out ROP, right? And what ROP is we basically find gadgets, which are small little assembly instructions like Legos, and we can use these Legos to build a giant payload. So the assembly instructions always end with a return, and what it does is it's just a bunch of operations that end with a return. And the reason why we want it to end with a return is because we're going to put the gadgets on the stack. We're going to put whatever values above that. If you know, the assembly instruction is popping something, which is what we're going to go for, we're going to do an instruction like pop rax return, right? So we put the gadget, we put the value that we want to be popped into RAX, and then return. It's going to pop whatever ESP is pointing to. It's going to pop the address off the top of the stack and return to that. And we can just make this address another ROP gadget. So let's just do that. We need to know a bit about our calling conventions in x86. And I actually have some notes from an unrelated war games I was doing with Ret2 systems. Oh, it's already open. So we can see here that we will need to pop. We're going to need to pop some stuff into RDI, RSI, RDX, and RCX based on the following parameters. Also, it looks like R8. So param 1 will be RDI, param 2 will be RSI, param 3 is going to be RDX, param 4 is RCX, and param 5 is R8. So we'll just need to pop these values into these registers, and then at the end of that ROP chain, we're going to call Vader, and all the parameters would have been set correctly. So let's start doing that in our script. We're going to be using a tool called Ropper to find all the gadgets, and basically that's just going to dump all the gadgets in the assembly or in the program, and we can just grep through it. Let's look at the source and go to main so we can find what that offset is. Okay, we see local 28 is 32. We're going to add 8 bytes to cover the RBP register, and the offset is 40, and it will overwrite the return address. So let's try doing that. I'm just going to quickly Python 3 times 40 plus b. Let's put 1, 2, 3, 4, 5, 6, 7, 8. Like that. And we see we've overwritten ret. We've overwritten where RSP is pointing to at the time of the return here. So if we press continue, we'll get a seg fault because this does not exist in memory. This is not a place the program can jump to. So we found the offset. So let's start off our payload with that offset. And next in our payload, we want to pop a value into RDI. And that value is going to be, we'll just stay in this function from now on, it's going to be dark. I'm just going to put small comments here to specify what the string is. So that's going to be actually after we put the gadget, because we're going to do the offset, and then we're going to do the gadget, then we're going to do what we want popped into the register that the gadget is operating on, and then we'll do the return address for the ret. So if this isn't making sense now, don't worry, it's going to make sense pretty soon. Okay, there we go. And let's grep for pop RDI. Okay, well, we can just do RDI, I guess. And we see one right here. I'm not sure why that didn't work. So we see a useful gadget right here. So let's quickly add that to our chain. Make sure we send the bytes as a string. Here we are packing it with the struct thing that is from Pwn Tools. And after that, we can put the value we want popped into RDI. And then after that, we can put the value we want popped into ret, which is going to be the next gadget. So what we want in RDI is this string. We can't actually put the string itself here. We need a pointer to that string. And that should be pretty easily to find just in memory. Let's actually open up GDB again. We can do it using that. There's a find tool in Jeff. And Jeff's just a GDB extension for binary exploitation. Pretty useful. Let's look at proc mappings because we will actually need that. And let's just check in the areas of the program where we might find that. I think it would probably be, I don't remember where the function is, but let's just check these address spaces. There's not that many. We will find it eventually. And let's search for dark. Pattern not found. Oh, let's try 200 to 400. There we go. So we got dark. That's now in our chain. Put this in here. Then we put the next gadget. So next we will be popping in our SI. So Robber, file Vader. Here we see the only thing we have is a gadget that pops RSI, pops R15, and then RET. That's fine. We can use this. We just got to make sure we add an extra junk value that gets popped into R15. Absolutely fine. Just take note that we're popping 2 registers, not 1. So we'll add this gadget to our chain. Then we'll do, this is what's getting popped into RSI. So this is what we care about. Next, the junk value. It could be anything. I'll just, I don't know. I'll just put dead beef in there. Because why not? Doesn't matter. And then we need to pop the return. So the next gadget we want is RDX. So let's search for RDX. Actually, here we have 2 registers that we need. We do need RCX, and directly after RCX we need R8. So this gadget is actually perfect. We can just finish it with 1 gadget. So that's fine. First gadget is, or the first value, which is RCX, is going to have to be the leet speak the, so TH3. Perfect. And the next part is going to be force with a 3. And there it is. So we just put this in here. And there we have it. We finished the chain. Now let's add the final return address, which is going to be the function call. So plus equals P64. And Vader, right here is where it starts. And there we have it. Do we need to do a read until? The only thing left to do is send this payload to the program. We're just going to do that really quickly. We need to read until we have a space and these 3 arrows, and then we can send the line. That should be it for our exploit. Let's make a fake flag file so we know it works, because the remote service is no longer up. It looks like the remote service is actually still up, so we could try sending it over there. P equals remote 0 cloud shells IO 20712. That's not what I wanted to do. And it looks like it works on the remote. Not sure why it didn't work locally. It's whatever though. It does work as we can see. We got the flag. There is no try. So this, again, was just a baby ROP. We can look at it one more time. We see we're just making a chain, popping gadgets, which are sort of bits and pieces of assembly that end and return instructions. And we're just using that to pivot throughout existing code that is already in the program and making it do what we want in a different way, you know, other than shellcode. So yeah, you can see how this would be useful if we needed to get a shell instead of just calling a function with parameters. If we need to get a shell, we'd obviously have to pass, you know, syscall numbers and all that. And that's useful because usually there are syscall instructions and useful gadgets to do such a thing, such as finding bin sh strings. There's useful gadgets and stuff like that in libc. So yeah, pretty useful. All right, so the next one we are doing is SATisfied. So let's run the binary here. We see it gives us a random token, alrighty, and it asks for a response. We'll just say, hi, and the program exits. So let's open up Hydra and take a look at the source. We see here we have a print flag function, and it looks like it does just that, prints the flag. We see print logo, we can guess what that does. We see main, and we see sat access and authentication function. Let's start at the entry point, which is main. It looks like what it's doing here is it's printing the logo. It's assigning the time of the local system to var2, and using the time it's generating a random unsigned integer, and it's generating another random integer, and it's passing this new random integer to ivar1 into sat access. So what it's actually doing here, I think it's creating a seed for the random function, which it's then using to make the ivar1 function. So basically this whole thing is just making a random number, or it's computers, so a pseudo random number, passing it to sat access. Let's take a look at sat access. We see here we have param1, which is going to be our random number. I'm just going to rename that for ease of reference, random int. And we see a buffer of 16, local 18, local 10. We see it says here's your random token. It gives us the random int that was made in main. Then it asks for your response. Here we see scanf being used vulnerably. It's unchecked, so we can overwrite local 28, which is 16 bytes, and write to local 18 and local 10. So we can overwrite this, write to local 18 and local 10. After that would be the return address, or RBP, and then the return address. We see here it's going to call the auth function, save it to var1, which is called before local 28, so we're not overwriting this. This is fine. So we call auth functions, get saved to this. If the result of lvar1 is not equal to 133 or 31337, I made this an integer. Originally it was hex, but I just find this easier to read. Then it's going to make a call to exit. Note that if it calls exit, it's not actually going to hit ret. It's going to call a libc function, which is exit. So our overwritten return address for this function will not matter if this call to exit is made. So our main issue here is we can overwrite local 28 via the scanf. We overwrite local 18 and local 10, which is used here to generate a number. However, although we can overwrite ret after this, it's not going to matter, because if the challenge response isn't met, if it's not equal to this, it calls exit. If it is equal to this whole if statement is ignored and it calls return, which we've overwritten. So what we need to do is we need to overflow local 18 and local 10 with the correct values so that this response is valid and this exit is not called. Let's go to auth function. And it seems it's just, what it's doing is it's taking local 10, or no, it's taking our param, so it's taking the random number that's generated on the server side. It's XORing it with local 10, and then it's bit shifting it to the left by this value right here. And this value is just going to be param2, which is local 18, I believe. Yeah, local 18. Local 18 and bitwise and with 3F. So there's a couple stuff we can do here to make sure this response is valid. The most easiest I think that we can do is we're going to simply set param2 to 0. We're going to set it to 0, and after that, this whole bitwise won't matter, because when you shift something to the left by 0, it's the same. So really the only thing we need to focus on is the computer generated challenge XORed with our parameter. And if you're not sure how XOR works, it is a computer bitwise operation. It's pretty easy to understand, but basically where stuff isn't the same, come on, can probably just pull up a nice image of this and I'll be able to explain it a lot better. Where stuff isn't the same, the XOR condition resultant is true. So it's just going to go through the binary of this, and the resultant is going to be based off of this algorithm. And mathematically, if you look at this, as long as you have two of the values, as long as you have AB or BQ or QA, it doesn't matter. As long as you have two, you can get the third value. So as we see here, if we had 1 and 1, we could see we get 0. If we have 0 and 1, we can get 1, right? Because 0 XOR 1 is 1, 1 XOR 1 is 0. You can see it works mathematically. It's just very simple bitwise logic, right? So we know that param 3 is going to be our computer-generated response. We don't know what param 1 is, what it needs to be. Of course, we're controlling that via the overflow in the last function. What we need to do is we need to make sure that this computer-generated challenge, so let's just call that computer challenge, XORed with whatever needs to equal 1337. As we said, as long as we have 2, we can easily get the third one. So what our exploit needs to do, it needs to read in this computer challenge, save it to a variable, and then it needs to XOR it with 31337. That's the value we're going to set param 1 to. So what we need to do is we need to do this calculation. Then we'll pass it as param 1. We're going to pass zeros as param 2. And param 3, obviously, the computer's doing that for us. So as long as we do that, the exit in the SATAccess function will not be called, and it will hit our return address, which, in addition to overwriting these, we've overwritten the return, and we can call the print flag function from that. So let's work on that exploit. So we got the challenge. All right. So our payload should be pretty easy. Let's see how much we need to override again. So 16 A's. Plus, what we need to do now is overwrite local 18. Local 18 is the second one. So parameters, when we're making a function call, x64 calling convention, the parameters are pushed onto the stack backwards before the call's made. Or I'm not even sure if parameters are pushed onto the stack in this calling convention. I can find that out very easily though. No, they're just popped into, they're moved, not popped, they're moved into registers and then there's called. But it's backwards, so first we call the last parameter, or we set the last parameter and then the next, etc. We can see that's happening here. So let's do this. First we're going to do local 18, which we're just doing as 0. And you may be saying, well, what about null bytes? That actually doesn't matter here. There's no string functions. The reason null bytes would be a problem is if there was a string function, because clib string functions interpret null bytes as end-of-line characters, so it would cut off the rest. But here we see it's just doing a scanf, so it's not going to care about that. So we give it a null byte. That way that there's no bit shift, otherwise this would be pretty annoying. P64, and let's just pass it to local 10. And after that, let's put B's times 8, overwrite RBP. And finally, the return address we want, which would be print flag. Here we go. Oops. Oh, okay. And everything looks pretty all right. So we overflow out of the 16-byte array. We pass 0 to local 18. Then we pass our response to the challenge in local 10. It computes it. Because the challenge is correct, that means that this if statement will not be executed, and it's going to hit our return address, which we've also overwritten. Good stuff. Let's see it work. Actually, I might need to create a flag file. I'm not sure if this again, I'm not sure if this is going to work locally. I do think the challenge server is still up though if it doesn't, so we should be fine. Yep, it worked fine. I don't need to do go to the challenge server. So yeah, there we go. We got the flak. Easy as that. Easy as that. Just a very simple, again, sort of reverse engineering challenge mixed in with this buffer overflow challenge. I thought this one was pretty cool. So yeah. Yep, so that's it. Really enjoyed the baby ROPS. Pretty fun. I really enjoyed the CTF in general. Thought there was a lot of cool stuff to learn. Lots of stuff to be done. I sure did learn a lot, and I got lots of practice in. So thanks again. I hope to see the FitSec team from Florida Tech back again next year with Space Heroes. It was fun. Good job to Corcrupt, and thanks for watching the write-up. Hope I helped you out some way today. I'll see you next time. Peace.